Your face is the one I tend to read the most, because if it's not confused, you show it. If it's not clear, you show it. Okay. So we've now taken a tour of many languages. Okay. And are we done with the tour? Are we done with the overview? Not quite. We might want to go beyond languages. Okay, this is something I started off with. I said, look, the conventional view of viewing a program is algorithms for data structures. When we added Prolog, we said, well, it's algorithms / rules plus data structures, where data structures are the facts. And then we talked about not having any of this stuff and being totally data-driven. Okay, that we give some example data, and we say, hey, program, from the example data, figure out what I mean. Okay? So a long time ago, when people were doing AI, they all wanted the DWIM instruction. Can you guys imagine what DWIM stands for? DWIM? Yeah, Robert? No. Do what I mean. Do what I mean. Okay. So this is and people threw that instruction as something that will never be ever implemented. I mean, they were joking. But we've come near that concept, that what I mean I give by sort of mentioning a bunch of data, and then statistics does the magic. Okay. And so what I might do is I might go and just give some examples of final score and total score combinations. And for each combination, I go and say what I would like to do with that combination. Is the person passing or not passing? False or true? Okay. And I give some header information to go and say that, look, the first item is total score, it's numeric. The second item is final score, it's numeric. And the third item is this thing I call attribute, I call pass. These things are called attributes. And it takes two values, true and false. Okay, and here's my data. So how many of you have done machine learning? So you know more about this stuff than I do. Okay. So what is the architecture? What is this data called technically? This data that I'm saying example, what do machine learning people call that? Training data. Okay. And training data is fed to a module that we will call what? Something has to go in, some module pre-built for us. Okay, so basically what I'm saying is that we'll take the runtime. We'll put everything to runtime, So this is done at compile time, this is done at runtime, and then we'll make the runtime so sophisticated that we don't even have to write a program. So it's given to, in this case, we want to say whether we have two values to choose between, pass and true. So something that chooses between two values would be called what? In machine learning terms? Sorry? Classifier. Okay. So we'll have a classifier. Okay. And we'll pass it some training data. And when we give training data to a classifier, what data structure does it produce? What's the technical term again in machine learning for the data structure it produces? We are overloading. We use the same term for something else earlier in the class. Model. Okay. But this is not our MVC model. Okay, so we'll go and say, by the way, we'll tell the classifier, we are trying to map the total score and final score to pass, okay? And it'll build a model. And then there is training data, and what's the other kind of data that we have in a machine learning sense? Test data. So test data will be our example. This is what we want results for, okay? So we'll go and pass. So we build model data from training data, which is sort of like compile time. Okay, we've done that, and now at runtime we want to go and say, hey, here's some test data. Please tell me how you classify the values, and hopefully what it comes up with is correct. Okay, that's the basic picture. That's the level at which we'll work at this point. I'll talk a little bit about the classifier that we're going to use. So how do you use this actually? I mean, you have to, if you're going to build an interactive program of the kind I talked about, we're not sort of, we want the kind of prompts, enter the total score, enter final score, here's the result. We want that UI. Hopefully our model view controller framework allows us to go and use the view and controller from before, and all we have to do is create a new MVC model, okay? And that new MVC model is going to now use this classifier that is going to be some library routine and do the classification of the data, okay? So making predictions on test data is sort of like runtime. Okay, so we go to UI. So we are not quite done with sort of programming. We have to still set up the MVC structure, but the view and controller are the same. We'll change the model. Okay, and the model is now going to take. So there are many classifiers possible. Okay, the model is oblivious of the exact classifier, and it takes in its constructor which classifier do you have, and there is this type called classifier. I'm using Weka, which is a Java implementation of the decision tree algorithm, which is like the most popular algorithm used in machine learning. And I'm going to, in my constructor, take the file that has the training data. So we're just looking at it a very high level black box approach. Okay, it takes the classifier, it takes the file, and it says, hey, build the model. Okay, so the constructor does that. It's done once. Okay, and then whenever isPass is called, I'm going to just inherit from my abstract pass model, and all I do is override the isPass method, and that's not going to compute anything now. It's going to go and say, call again another routine, which I'm calling predict string. The Weka util is something I wrote because the Weka library is more low level than it needs to be for this example at least. So both build tree model and this predict string are things I wrote as abstractions above the Weka library. Okay, and this one says predict the string. Okay, and it says here's the classifier that you should use, whose model I've already built. Here are my input feature names, and that I've got as an array, total score and final score. And here are my feature values. So it gives you the feature names, input feature values. It gives you the output result attribute name, which happens to be pass, I guess. And then it says so result value names. Okay, it also tells you what values that attribute takes. Okay, it says pass takes true and false values. Now that stuff is in the Weka file, so I don't exactly know why I needed to give it again to the low-level routines. But they required me to do so, and I didn't build an abstraction that reads the file directly. So, and then I go and say, okay, give me back the value, and if the value is true, I'll print it one way, or if it's false, I'll print it another way. Okay. So you understand now the basic architecture of this magical tool. We'll look at some of the statistics behind it later. Okay. Now, Weka util. So what I'm showing you guys code, and I know to really understand something, you need to look at the full code, and you may want to actually implement it. So I have some slides that is just details I won't go through, but if you want to and this stuff is also available in my Git repository. But so here's again, we are building a model in the constructor and making predictions on test data. But here's some details that I don't want to go through, but if you want to just look at them to understand what's going on underneath, you can do so from the slide. Okay. So the question then is, given this problem, how accurate do we think this most popular classifier in the world is? Okay. And I gave it some data in the beginning. I didn't think too hard about the data, and it was horrible. And it almost never predicted right. I said, how can I even introduce this concept if I can't make it right? So I said, well, that's fine. We'll just say that's a problem. But then I decided that I was going to show the slide to you guys and ask you to figure out what the algorithm underneath is. Yeah.
You said that you ran it and it didn't go out well. Was it 50% or was it more or less?
So I didn't do anything rigorous. I just went and tried some data interactively, and it was coming up with false, the wrong answer almost every time I entered something. Okay, I didn't try to do any analysis there. But I'm telling you, the good news is coming. Okay, so then I said, who's at fault? Me, my examples are at fault, or the algorithm is at fault? So then I said, okay, then I had this idea that I'll ask you guys at the start of class, what do you think is the underlying algorithm? So then I tried to put myself in your shoes, and I tried to give you a sporting chance. So I added some more data. Then I said, human beings know that higher scores mean more likelihood of passing, and lower scores mean lower likelihood of passing. Weka doesn't know that. So I try to add some more data to make Weka also understand that. Okay, and that's when I came up with this data. And I said, whatever result comes out, I'll accept it. And I tried to make it, see what happens. And the first few values I tried, they were all right. I said, well, surely that can't be correct. Some more values, they were also correct. I just couldn't make it fail. Okay, so that was pretty good. That this stuff can work. Now I think you guys could have predicted with fewer data, but this is why the world is going towards this direction. Okay. So it was chancy, right? Who knows the statistic whether the answer is correct or not? And in computer science, we spend so much time on correctness. Correctness of our algorithms, correctness of our bounds, we have proofs. And here we're using inferences. We are saying, yeah, maybe we're right. And people have used all kinds of terms for inferences. They're really, if you're a systems guy, you just call them hacks. But if you're an AI guy, or if you're an English person, you call them guesses. But AI guys have used the word heuristics for this, which is sort of a more classy term for it. And the question arises, assuming that we are willing to write code. Okay, we've got degrees in computer science. We want a job. We want jobs. So, assuming we're willing to write codes, why would we ever go the inference route? Why would you go a route where we don't quite know whether the answer is correct or not? Yeah. It could be a lot faster in terms of code development.
No, in terms of actual time to run algorithms versus.
So you think the runtime, the computation time might be faster? Depending on the problem. You guys who've done machine learning, what do you guys think, Hutch?
Maybe like there's a pattern that you haven't thought about before, like with financial models, you can find correlations between certain things you might consider.
So maybe you weren't smart enough to figure out you don't quite know. You don't quite know what algorithm to use, right? What about you machine learning guys? Is machine learning algorithms fast or slow or in general?
Very slow, but
Well, typically the word big data and machine learning go together. Big data requires a lot of processing.
So they're really slow to train a model, but
To make the prediction? Okay, so that's an interesting point of view.
there's some papers on like networks that can do like sorting in event time with pretty high accuracy.
Okay. In what order of?
Yeah, linear time, like rather than analog and.
Really? So the point is, for something like decision tree, it comes out with an algorithm from the training data. It comes out with exactly the if-then-elses it uses. If you could write those if-then-elses yourself, then it wouldn't be any faster. It wouldn't be any faster, right? But you're saying that sorting programs, most likely, and their accuracies were how good?
If you get, it's easy to come up with training data, you can get it up like upwards of 100% almost.
Almost 100%? Okay, that's interesting. So I was learn. So guaranteeing something is a little slow, okay? But you're saying in practice it can happen. So that's an interesting thing, but the training data, that time takes, so right now I actually have students working on this stuff, and what we are doing is bound by the amount of time we have to do training. So training data, it can be an issue, okay? But you're right, that's done only once. But a lot of researchers in machine learning are trying to make the training phase fast. So that time must matter, right? I don't know if it matters or not, but from the research point of view, it matters. I don't mind waiting 3 weeks for something to be trained. I know it to figure out a bug in programs sometimes take me 3 weeks. So I'm happy to wait 3 weeks. Okay. So then the issue became that we may not know all the correlations, and that brings me to something else. There might be proofs that say that we can't do things. There are proofs to show that we can't do n-log sorting in less than n-log n time if we want to be 100% correct. And yet, we want to do better than that. there are proofs that say we can't tell whether a program halts or not. Yet, I want to go and test your programs automatically, and part of the testing involves determining whether you halt or not. So yes, I'll make inferences, I'll make hacks, I'll use heuristics so that I can get the job done, okay? And which in practice can work pretty well, okay? No guarantees, but they can work in practice, okay? Just like the sorting example that was mentioned, okay? So that's one reason. And the other one was what you were talking about, that we don't quite know the correlations, okay? So if we want to detect whether, you know, the stock market is going to go up or down, we don't know what algorithm, if anything, we don't understand how human beings work, okay? And we want to tell whether a human being is happy, frustrated, in difficulty, we just don't know. So we just use statistics to figure out whether our guesses are correct with what the human being is feeling, okay? So that's where machine learning also helps, okay? And so from a programming language point of view, how is that interesting? A, it's programming by example, which is a term, technical term in programming. Also, we can make programs themselves be data on which we make inferences, okay? So we have these two worlds. We can try to unite them by making inferences on the programs themselves. And this is an area that people haven't explored much. I told you that even though I know very little about machine learning, I have students working on machine learning projects. I'm happy to use existing algorithms, but I'm very interested in knowing what inferences I can make about programs, okay? And so that's another relationship between programming languages and programs and machine learning. Okay, and I'll actually give you an extra credit project based on this insight. Okay, so let's back off. We've taken this tour. And based on this tour, we've come up with several new concepts that I've mentioned here. Okay, functional, only prefix operators, and so forth. And all these concepts came around because we looked at different programming languages. Okay, except for the decision tree, where we looked at no language. So the question I want to ask is that, you know, but many of these concepts occur in popular practical languages. You can have expressions return values even in Java and C. So it so happens that we saw these different concepts by taking a tour of different languages, but we were not really studying different languages. I mean, if you're studying different languages, you just get into syntax. We are really studying different paradigms of programming. Okay, and so we are studying alternative programming paradigms. Okay, if I teach you ifs and then I teach you fors, they are not alternatives. Okay, you need to use ifs in certain conditions and you need to use fors in other situations. But if I teach you recursion and I teach you for, I've got an alternative. Okay, and we can discuss the pros and cons of these alternatives. We can discuss how they're implemented and so forth. So we're really looking at programming paradigms. So this programming language, to call this a programming language course is a bit of a misnomer. It so happens that these programming paradigms were invented in the context of different languages. But ultimately, if you're going to do them in a scholarly way, we're looking at paradigms. Okay? So that's what this course is going to be about. That's why, you know, we'll be doing this Lisp interpreter for many projects, just adding new and new concepts to this particular interpreter, which come from different languages, in fact. Okay? So if you're looking at